Thanks for joining me. My name is Savin, and most recently I was at Netflix, where my team was tasked with making sure that our data scientists were happy and productive. And I'm pretty sure, sort of like many of you in the room, will have similar job responsibilities as well. And if, like me, if you have tried to sort of like Google for what are the latest and greatest machine learning tools that exist that you can provision within your organizations, it's very likely that you'd have been greeted by a chart of this sort that tracks like maybe hundreds, if not thousands, of different tools that are coming up. And we were at the same spot a few years back at Netflix where we were trying to figure out what is the kind of tooling that we provide to our data scientists so that they can reliably get their work done and be happy at the end of the day about their productivity. Now, it's really important for us when we are deciding what tools to bet upon to look back in the past, look back at the recent history, because as one wise man said, if we don't know where we have come from, it's really difficult to predict what the future holds for us. So now, if we look at, let's say, the last 20 odd years of progress in machine learning, there are a few key macro trends. There are many things that have sort of like enabled more and more adoption of machine learning. Of course, on the hardware side of the house, 20 years ago, public cloud was not a thing. And today you can actually jump onto AWS, Azure, Google Cloud, many other cloud vendors, and you can get access to the latest and greatest of hardware. Just recently, Cerebrus announced sort of like, the release of their dinner plate-sized chip targeted towards building large language models. So now, independent of the size of the company, you can get easy access to the latest and greatest hardware very easily. And along with hardware, there have been immense progress made on the data platform side as well. Earlier, it was really difficult to even manage gigabytes of data, but now you'll find sort of like, even the smallest of startups, even like our startup as well, where managing terabytes and petabytes of data is becoming more and more easier. Storage costs have dropped significantly. Most organizations, they are using some kind of a blob store to store all of the data that they are seeing over many, many years that their businesses have operated. So things have become sort of like a lot more seamless on the data platform side as well. And of course, compute has also become a commodity. You can log into your cloud console and you can request, like hundreds of instances, and you don't have to wait for your hardware vendor to actually ship you instances, and then somebody has to go to a data center to hook up those instances and get things done. And then alongside that, there's an amazing library ecosystem as well that just did not exist even, let's say, 10, 15 years ago. I remember when I first started working professionally, my first job was to implement certain papers and sort of like, train these models based on sort of like the algorithms that we were writing by ourselves. And these days, practically nobody does that. And you can very simply just do a pip install PyTorch or TensorFlow and get things going. But then on the other side of the spectrum, now you'll see sort of like, machine learning being used in a much more variety of use cases. The sheer complexity of models has increased tremendously over the last very many years. These results, they matter a lot more. These models are being used in many critical functions as well. So whether it's, let's say, surgical AI, where your AI models are guiding a surgeon in terms of sort of like, doing some precision surgery, or whether it's driving or like, autopiloting self-driving cars as well. Now these results, they really, really indeed do matter quite a bit more than, let's say, like 20 years ago. And of course, there are now a lot many more people as well who are building these models. If you even look back, let's say 5 years ago, 10 years ago, it was really difficult to even come across good data science talent. And now most major universities, including UT Austin, has sort of like, dedicated programs around data science as well. So now we see more and more people getting into this ecosystem as well. And then of course, people used to say that software is eating the world, and now people are saying that ML is eating the world. And organizations by themselves, they have increased appetite to apply machine learning to even the minutest of business decisions that they come across. What that means is that over the last 20 years, many of the machine-related problems that have gotten easier and easier, and now what we are presented with tackling are the people problems. So if you look at sort of like the spectrum of machine learning progress, we have been sort of like making steady progress from answering whether something is feasible, whether something is possible, to questioning it should be actually easy enough to do certain things, right? And that's sort of like the trend that we have been observing. And as part of this trend, what's really happening is if you look at sort of like the progress that's being made in academia, the progress that's being made on the hardware side of the spectrum, our sheer technical capability, that has been increasing at a much more rapid pace. So the supply of machine learning capabilities, that has been increasing very rapidly. And the demand is also commensurately increasing. And even people may argue that the demand is increasing at a much more rapid pace. But they haven't really intersected right now. And the big sort of like gap today is this gap of productivity. Can we essentially make sure that our data scientists in any organizations, they are able to essentially take care of all the technical capabilities that are available to them in an easy and straightforward manner, so that they don't have to sort of like muck around with the infrastructural complexities or the ML complexities of the world. And that's pretty much sort of like where we found ourselves. Where when we sort of like surveyed our data scientists, they had access to the latest and greatest of research. They were responsible for much of that research as well. They had access to all the great hardware that organizations like Netflix could get access to, and more increasingly, even a small startup sort of like gets access to the same kind of hardware as well. But then there was still something that was missing, that was preventing our data scientists to be as productive as they would ideally like it to be. And that's where my team essentially sort of like jumped in to identify that, okay, how can we sort of like fill in this gap of productivity? Now, let me walk you through how we sort of like thought about this problem space concretely. And then I'll follow up with a project that we created in response to this problem, which we ended up open sourcing. And I'll give you a high-level overview of the project, and then we can open it up to questions. So it's fair to assume that everybody in the room is familiar with Netflix. Netflix has been pretty active in the machine learning universe for well over a decade now. They first started with recommending what DVDs people should sign up for so that Netflix can mail those DVDs to them. And then when Netflix pivoted to streaming, the very first machine learning product that they shipped was machine learning recommendations. But then over a larger period of time, as the business matured, there were many other areas of ML that Netflix started investing in. You can imagine even before Netflix has to recommend you what content to watch, it needs to recommend its internal content execs what content they should be licensing, what content they should be producing. Once they have made a decision that, okay, like maybe there's this new script called Stranger Things that's super promising, then somebody needs to make a decision about like, okay, how do you sequence the shoot schedules? Somebody needs to make a decision about like, okay, what is the probability that the show is going to be a breakout hit, and how many marketing dollars should be allocated to that particular show? How do we make sure that all of our content distribution boxes are cached with this piece of content wherever we predict that this piece of content is going to be rather popular? How do we predict user churn? How do we fight fraud? How do we make sure that anytime we are processing payments, those payments are successful and whatnot? So like, if not, thousands, like definitely hundreds of very deep machine learning problems that Netflix sort of like, suddenly found itself in. And it was my team's responsibility to figure out that, okay, how can we service all of these data scientists? How can we make sure that these data scientists, they don't get bogged down by the architectural complexities of an organization like Netflix? And to do that, it's important for us to sort of like, also understand that, okay, what is common across all of these machine learning projects? Of course, we can go out and build a stack that is bespoke to, let's say, the recommendation universe, or let's say, the content popularity universe. But given sort of like the sheer diversity of different problems that we were sort of like involved in, it would have been really counterproductive and wouldn't really have provided us the leverage. So in search for like, the common elements across all of these different projects, the first thing that was important was like, all of these projects need data, right? Some projects need tabular data, some other projects need unstructured data, many other projects were processing images and video assets that Netflix was maintaining. And we wanted to sort of like provide a way where the data scientists could have very easy, quick, and efficient access to these data assets. without actually worrying about where were these data assets stored, how to actually query these data assets. We didn't want a data scientist to turn into a data engineer to figure out the complexity of data transport or data movement. Another key important facet is that all of these projects, they also needed, they were executing algorithms that were highly compute intensive, and it was very likely that their laptop just may not have the kind of resources that many of these algorithms would need. Maybe they need access to a lot of GPUs, maybe they need to train multiple models in parallel, and it may not be feasible to just execute that entire piece of training routine on their laptop. And now, many of these machine learning projects, they also sort of like resembled what you would call a workflow. There could be sort of like multiple steps that would have to be executed. Maybe sort of like, in one project, you get access to some data, then you process that data to generate some features, and then maybe you are training, let's say, 200 models, one for every country that Netflix is active in, and then you're deploying each of those 200 models. Or maybe, let's say, you're responsible for predicting whether a user is going to churn or not, and you need to sort of like calculate their lifetime valuation and churn through all the data that we have collected about a given user over, let's say, the last 2 years. And that can be a huge amount of data, many different steps as well. So people essentially wanted to sort of like easily create and execute these workflows. And more importantly, many of these projects were being worked upon by teams of data scientists. So collaboration was a really important aspect for us. We definitely wanted our data scientists to operate in a world where they couldn't sort of like, just say that, oh, like this worked on my laptop, tough luck that it doesn't work on your laptop. We wanted to make sure that there was sort of like this core aspect of reproducibility, or more appropriately, rerunnability, that was baked into whatever we were providing to our data scientists. And they were able to essentially collaborate with people as well as run multiple versions of the same project so that they can effectively experiment at scale. Now, another sort of like key aspect of data science activities at Netflix was that there wasn't sort of like any kind of standardization in terms of what kind of frameworks people could use. Of course, all of these frameworks, whether it's TensorFlow, PyTorch, Scikit-learn, they have their own strengths and weaknesses. And we wanted to make sure that we are being relatively unopinionated with regards to the frameworks that our data scientists wanted to use. Being an infrastructure engineer, being a platform engineer by myself, I wanted to make sure that our team was responsible for making sure that we are being opinionated about the infrastructure stack, while our data scientists have the freedom to operate on the machine learning stack, and they can make those decisions because they are indeed the subject matter experts at the end of the day. And our goal here was that, okay, can we sort of like address all of these common concerns in a single framework? And now it's also important to understand, at Netflix, and this may be true at many other companies as well, that there may not be sort of like a single ML stack at the end of the day. It could be the case that maybe sort of like you have a single data warehouse, maybe you have multiple data warehouses, you may have multiple query processing engines. At Netflix, we were using Trino and Spark, and then we had our data warehouse built on top of S3 as well as Snowflake. So there are like multiple different sources of data. Then when it came to compute resources, we had sort of like teams that were using an internal compute orchestration system called Titus. But then, of course, given sort of like the general unavailability of GPUs, Netflix also had its own fleet of GPUs. So we needed to sort of like integrate with that as well. And then for those of you who come from larger organizations, like every single organization beyond a certain size has like at least like 10 different workflow orchestrators as well, and for different use cases and different purposes. And that was indeed the case at Netflix as well. And then, you slowly sort of like start getting into the realm of things that machine learning engineers or data scientists really care about. How do we structure the code so that there's proper versioning? How do we architect our code so that it can scale out well? How do we think about, this new field of ML ops so that once we have sort of like built a training routine, then it can be managed and these models can be managed much more effectively? Do we need to care about experimentation management tools? And then there are sort of like, a bunch of those. How are we hosting our models? Do we need to have a custom microservice, or can we use something off the shelf? That can also depend from your use case to use case. Maybe for your recommendation use cases, you really care about strong SLAs. Maybe some internal dashboards that are being powered by some of these models, the SLA may not be super high, so maybe you can use a different set of tools for that. And then as you sort of like go up the stack, then we sort of like, come into the world of these training libraries, right? And then that's where sort of like many of the data scientists, they have their own express opinions. And then there's the entire world of IDEs as well. Some people, they really like notebooks. Some people want to be in the universe of R. Some folks, they want to use PyCharm. If you are like me, then you're entirely on Vim. So there isn't sort of like a canonical ML stack even within sort of like any single organization. But what's really interesting is that there's sort of like this natural division of freedom and responsibility. As a platform engineer, we really care about how the data is stored, how the data platform is architected, how jobs are being scheduled on top of your compute platform, how is your workflow orchestrator deployed, and how much do we care about cost versus reliability versus if you look at from an infrastructure point of view, we couldn't care less if our users wanted to use TensorFlow or PyTorch or if they wanted to roll their own algorithm implementations. And from a data scientist point of view, it was exactly the reverse. They didn't care about whether the organization had invested in, let's say, Snowflake or Databricks, or they rolled their own data platform. What they really wanted was access to data as quickly and efficiently as is feasible, and a complete awareness of what are all the data sets that exist within my organization. Most data scientists that I've spoken to, they don't want to be experts in Kubernetes, but they do want to make sure that if they have a training routine that needs access to certain kind of resources, then they are able to access that as quickly as feasible without really sort of like getting into the weeds of how do I request these resources. Similarly, folks don't really want to sort of like interface directly with a workflow orchestrator. They have done their work. Now they want this work to execute, let's say, at some particular cadence every single night or whenever sort of like, fresh data is available. They would want ideally all of their versioning concerns and their scaling concerns to be taken care of. But then when it comes to figuring out that, okay, how do I translate a business problem into a mathematical model, that's where they do indeed want to express their opinions, and they would ideally want whatever tools that they are using to disappear in the background so that they have complete expressivity. So that's basically sort of like what we try to address. So we built this open source project called Metaflow, which we open sourced in December 2019, which was designed as providing sort of like a coherent interface to all of these concerns. And over the next 10 odd minutes, I'll just go over sort of like some of the high-level ideas that are baked into Metaflow. Many of these ideas, even if you're not using Metaflow, they may sort of like come in handy as you go about designing your own machine learning infrastructure stacks. So let's talk about a project lifecycle, right? Like so you have a data scientist who is able to experiment, let's say, within the confines of a notebook on their laptop. And let's sort of like walk through what does it mean for them to take that piece of work and move it into production. Now, I'm very well aware that the definition of production may vary from person to person. For some people, it may be that, okay, like I've trained this one model, I want to just generate some output from that model and maybe write a memo so that the execs can make a business decision. Maybe that model is going to generate an internal dashboard, or maybe that model is going to sit in front of a tier 0 service serving recommendations to the entire world, so the SLAs are going to be super sky high. Maybe there are, let's say, tens or hundreds of data scientists working on a single model, and how they collaborate effectively, maybe that's sort of like, the most important aspect for a production grade machine learning model as well. So let me walk you through sort of like all of those different facets. So of course, like a data scientist, they like to explore with notebooks. They are great for exploration, but they can very quickly get messy. And at that point, our recommendation for our data scientists at Netflix was that, once you're happy with something that's working on your laptop, on, let's say, a limited set of data, then it may be helpful for you to sort of like, just go ahead and create a workflow out of it. And we wanted to make sure that creating a workflow was as simple as feasible. So in this particular example, you can see that we have this decorator called step, and the step decorator will essentially denote the nodes of your graph. And so the two nodes in my graph are the start node and the end node, and then the start node essentially has a pointer to the end node. So with very basic concepts. You're able to sort of like just copy paste code from your notebook and create a very simple Metaflow flow, which you can then very simply just execute directly. And then Metaflow will execute this on your behalf. Now, there are many other sort of like tools that provide sort of like workflow orchestration capabilities, and we wanted to provide an immediate benefit when the user sort of like does that. So what Metaflow will do behind the scenes is that it will essentially go in and snapshot all the internal state for you, so that then you can step back in time and you can go and say that, okay, like I want to look at my workflow that I executed, let's say 6 months ago, and I want to get access to the model. I want to plot what my metrics were. I want to view the logs, or maybe let's say my colleague is doing some work and I want to access their models and whatnot. So Metaflow will essentially, by default, version everything for you. So you don't have to sort of like be an expert in Git or even sort of like actively track any of your work through any other tool. And then you can essentially just use your Jupyter notebook to inspect all the work that you have been doing or any of your colleagues have been doing. And that sort of like fosters some immediate sharing of results, as well as keeps a running log of all the work that's been happening. Now, once you have sort of like, created a workflow, it could very well be the case that maybe sort of like, your laptop doesn't really have enough memory to process the data that you are interested in. And at that point, you may want to sort of like, just spill over into the cloud. So with yet another decorator, you can very simply just state that, okay, like this particular step, we want this step to run on an instance that has, let's say, 128 gigs of RAM. And then what Metaflow will do is it will essentially run this particular step on, let's say, a Kubernetes cluster or an AWS batch compute environment for you, and it will move all the data around for you. So in this particular scenario, what will happen is the end step will run on your laptop, while the start step runs on an instance that has 128 gigs of RAM. And then let's say you were processing a huge data frame in the start step. That data frame, that processed data frame, is now available to you on your laptop as well inside the end step. So you're able to sort of like then mix and match different instances to get your work done in a very seamless manner without actually being an expert in Kubernetes or Docker or moving data around between sort of like, many of these different instances. So that's all great. Then the next problem that many of our data scientists ran into was that, okay, like we can sort of like scale vertically, we can get the largest of instances that are possible, but we still need to train many models. We need to train a model for every country and language that Netflix operates in, which sort of like is upwards of 1,000. Maybe, let's sort of like also roll in some hyperparameters as well. And suddenly you're looking at like a data scientist wanting to train, let's say, thousands or tens of thousands of models. So we wanted to make that, again, super simple and straightforward for them. So in this particular case, the train step, you will essentially run 100 copies of those 100 containers, each of them with 128 gigs of RAM. You can swap it out with GPUs as well. And that sort of like very quickly provides our data scientists immense capabilities to sort of like do really heavy duty machine learning processing. So now that, like with Metaflow, people are able to essentially get access to data, get access to compute in a much more easy manner. The next bottleneck that presents themselves is that, okay, how do I sort of like make sure that, the super expensive GPU instance that I'm launching on the cloud, that doesn't get starved for data, that I'm able to move data, let's say, from my S3 storage to this compute instance as rapidly as possible. So we've introduced sort of like, many tools within Metaflow that will provide you upwards of 10, 20 Gbps of throughput between S3 and your EC2 instance, for example. And what that means is that many times it's actually faster and much more efficient to communicate with S3 than the local disk that's attached to your instance. And that sort of like, suddenly unlocks many new use cases for our customers. So you can imagine sort of like, somebody, let's say, they want to use Spark for some data processing, so they can fire off a Spark job from within Metaflow, and that Spark job can land some data as Parquet files within your S3 storage, and then Metaflow can pull those Parquet files immediately to your GPU instances, and that sort of like, again, make sure that, like as an end user, you don't really have to care about like, okay, what is the most efficient way to move data around, but then at the same time, you're able to get access to really highly efficient and cost-effective compute. So I'm running short on time, so I'm just going to race forward so that we have sort of like, a few minutes for questions. So once we have dealt with compute, once we have dealt with data, the other sort of like big issue is that, okay, how do we think about dependencies? I want to run some compute on a remote instance. How do I get my favorite packages over there? So again, decorators to our rescue, you can annotate any given step with the dependencies that you need, and then Metaflow will make sure that there's a stable execution environment that cached for you. So even if, let's say, for some reason, Google decides to yank away TensorFlow, the fact that Metaflow will manage that environment for you means that now you can have this workflow that's now hermetically sealed. Metaflow logs your code, your data assets, all the metadata about the execution, as well as your execution environment. What that in theory means is that now I can actually look at my colleagues' work and I can very reliably execute that and have like good chances that, okay, this workflow is actually going to run till completion. So that's all good and fine. Now, I have a workflow that can scale out to the cloud. I have a solution for data. I have a solution for libraries. Now I want to run this workflow, let's say, every single night, whenever, let's say, at midnight or whenever my workflow sort of like needs new data. Now, most organizations, they have some kind of data engineering workflow orchestrator, Airflow, step functions, Argo workflows, and whatnot. The good thing is that they execute a DAG, and with Metaflow, you have written a DAG, so we can very easily compile a DAG for you that can essentially just be executed seamlessly. So you can just do Airflow create, and Metaflow will create an Airflow DAG. Can do step functions create, will create a step function state machine, and similarly for Argo workflows as well. There are a bunch more functionality within Metaflow. You can very easily run A/B tests and have multiple versions. Let me sort of like skip through that. Now let's say you're able to sort of like get a workflow running. Now things will fail, and we provide sort of like many tools for users to be able to sort of like either prevent those failures or be able to debug those issues. So you are able to sort of like retry failures. You're able to catch certain failures that you expect may happen periodically. But then more importantly, the fact that we are able to capture the entire intermediate state means that, let's say you deployed a workflow on Airflow, then you're able to actually resume the failed workflow on that executed on Airflow locally from the failed step, so that then you can actually replicate the issue that happened. And that essentially then provides a much more easier and simpler way for people to replicate the failures and then fix those. And once those failures have been fixed, then they can essentially republish the DAG on Airflow. So that's Metaflow. I'll just keep the slide up so that then we have some time for questions.
Thank you so much, Savin. All right, we're going to start with some questions. There were a couple questions on Slack, which my co-host Madikan here will read for us. But I wanted to just start off with the room. If there's anybody here who has a burning question, I'll walk over.
Hi, just based on the workflow you described, what are the, as an end user, one of the pain points I could see is actually having to cut and paste from a notebook to a Python file, and especially if I have to go back and correct the algorithm earlier.
Sorry, can you remove your mouse?
Okay, but to, I guess one of the pain points is the fact that you have to cut and paste from a notebook to a Python file, and especially if I have to repeat the cycle because of an error or something like that. I would have to repeat that process. Have you ever thought about using tags or Python magic so that you can work directly from the notebook and skip that cut and paste step?
Yeah. So you can definitely sort of like execute a Metaflow flow within a notebook as well. So you don't necessarily have to sort of like go between a notebook and a Metaflow flow. And every sort of like functionality that we have baked in is designed in such a manner such that you can actually sort of like develop your Metaflow flow interactively as well. Okay. So you're able to sort of like write a workflow, execute it, let's say it fails at a certain point, then you can resume your workflow from the step that it failed by fixing in the failures, and you can sort of like iterate very quickly from within Metaflow as well. Okay. And then of course you can execute a Metaflow flow within a notebook too.
Thank you.
Just doing a quick look around the room. All right, I'll come to you next. I'm just gonna do a virtual first. Madika?
Okay, we have a question from Zachary, and Zachary wants to know, I'm curious what recommendations you'd give to college educators training students who will eventually start as junior engineers within this kind of data science work. What do you wish was taught?
Yeah, definitely. I mean, there are like many dimensions to that question. The big one would be that usually there's a big difference between data science that's taught in school versus data science, how it's practiced in the professional life. So making sure that people are well familiar with that. most of the time it's not about sort of like, the fanciest algorithm, or just getting access to the largest of the data sets, but operational concerns and the operational pain points are real. And educating people about the realities of real-world machine learning is really important.
Next question.
Yeah, very nice talk. Can you talk a bit more about the back end, like how it's done? Maybe just in a few words, I'm very interested how you do it,
sure,
and
sure.
how you store the relation between the task and do the...
Yeah. So, I mean, the good thing is that it's an open source project, so you can go and sort of like, look at the code, and we are happy to sort of like address specific questions in our community as well. So it's a Python project. Basically, we provide an SDK so that people can write these workflows, and then behind the scenes, we rely on sort of like many amazing Python primitives to farm out compute to the cloud and make sure sort of like, all the state is managed by Metaflow behind the scenes. Now, to get started with Metaflow, it's actually very straightforward. So you just need to do pip install Metaflow, and then you get the capability to integrate with the cloud directly. There's a small web service as well that we ship, and that's needed if, let's say, for whatever reason, you want to share your work with your teammates so that there's sort of like a shared storage that people can sort of like access. But that's essentially the deployment footprint that we have. And then, of course, if you want to deploy a UI, then that's yet another service. But by and large, that's sort of like the architecture.
Okay, we have another question from online. This is from Nitish, who wants to know, how easy would you say it would be to apply Metaflow to existing projects and infrastructure, or would you recommend using it from the get-go for new projects only?
Yeah, I mean, like for people who are starting out with Metaflow, our recommendation is always to sort of like take an existing project, move it to Metaflow, and then, like be convinced of the benefits. Because at that point, you can essentially sort of like compare Metaflow with whatever sort of like existing stack you had. And that's sort of like the easiest and quickest way to identify whether Metaflow is for your organization. Now, if let's say, you work at a startup where you are a solo data scientist, and most of the times you don't really need to get out of the confines of a notebook, then it may be sort of like rather difficult for you to sort of like really appreciate the value that Metaflow may bring in, and maybe sort of like Metaflow may not be sort of like rather useful for you at that particular point in time.
Great, thanks. I think there was one more question from the audience, and then we're going to go to the next talk.
So I think you briefly talked about it, but did you say that Metaflow like has its own process for version control?
Yes. Yeah, so every single time you execute a Metaflow run, we will assign a unique run ID to it, and we'll log the actual code that you were executing, so you don't have to rely on Git. We'll tag that execution. It will have all the metadata, including your username, the date you executed, all the data that flowed through it. If, let's say, you generated a model or any data artifact as part of your execution, then all of that gets snapshotted. So you can go back in time and you can be like, hey, I need to look at this. Like, this is a real story at Netflix as well. We had an intern who joined us, and they were using TensorFlow, and then the next year they were a returning intern, and in 1 year TensorFlow had moved well beyond. And of course, the first thing that they ran into was that, okay, I can't even get access to the older version of TensorFlow because the transitive dependencies have moved and whatnot. But the fact that they were using Metaflow meant that they could easily go back in time and use sort of like all the work that they had done a year ago and start building on top of that, and not sort of like spend, let's say, a week, 2 weeks of their 10-week duration redoing all the work that they did in their previous internship just so that they could sort of like make further progress. So that's the power of sort of like, ensuring that there's some amount of rote rerunability baked into the system.
Great, thank you so much, everybody, for your questions. We do need to move on and get ready for the next talk. I would encourage everybody, if you have more questions, please post them in the questions channel. I'm sure the speaker would be very happy to answer them. And thank you all for attending.
Yeah, and I'll be around if you have any questions. Happy to take this.